Hi, I'm Karthik Suresh from University of Regina, here to talk on the topic Detector Design Optimization using AI for the HAEIC detector. I've set up the talk in the following order. I would discuss the Electron Ion Collider, the next generation particle physics facility that is envisioned to be built in the next decade. I will specially talk on the HA Proto collaboration along with the generic detector system proposed to be built. I will then move on to one of the sub-detector system, namely the inner tracking station proposed by HA. I will lay out the details of the detector system and introduce the problem in hand. I will then talk about the method of multi-objective optimization along with the idea of genetic algorithm, namely the NSGA2 algorithm. Finally, I'll show the result of the AI in optimizing the detector design for HAs in a tracker. In the end, I'll talk on the summary and the next steps of this project. EIC is the next generation particle accelerator facility proposed to be built at Brookhaven National Lab with a combined budget of about $2 billion. It would make use of the existing infrastructure at RIC and BNN. The main physics goal of EIC is to understand the glue that binds us together, the gluons. It aims to study the structure and dynamics of matter at really high collision rates with polarized beam of both hadrons and leptons. The whole machine would be capable enough to perform high luminosity measurements of the order of 10 to the power of 33 to 10 to the power of 34 barns inverse second inverse. EIC detector system will be able to offer a flexible center of mass energy range between 20 to 140 GeV, which is broad enough to explore sufficient resonances. Also, EIC will be equipped to deliver highly polarized beam of leptons and hadrons, which collide to produce a ton of particles in all directions and varying energy. These particles will be measured using nearly a 4 pi detector that will be constructed. EIC has two interaction points, namely the IP6 and the IP8 in its proposal. The colors here represent different storage and collider ring for the hadrons and the leptons that will be accelerated in the facility. In order to meet the broad expectations of the EIC physics program, HA was formed. HA comprises of more than 80 institutions currently. HA aims to develop low risk, cost effective detectors where we consider reusing parts of detector technology wherever possible and demonstrate the performance both at IP6 and IP8 interaction points. HA aims to provide the detector concept for EIC for both the interaction points using a 1.5 Tesla solenoidal magnet. HA consortium comprises of different working groups actively working to meet the EIC performance requirements. You can see here different working groups interact with each other, which is very crucial, especially during this time of the experimental program, which is in its design phase. I'll show how computing team works in collaboration with others in a while. Here is a generic EIC detector that is being proposed. As you can see, the setup is nearly a 4 pi detector, having calorimeters on either end to measure the energy of the final state particles. There exist a bunch of PID detectors like the Dirk, Emrich, and the DRIDGE to identify the type of particles. The inner part of the detector will be surrounded by the 1.5 Tesla magnet, and inside of that 1.5 Tesla magnet is where we have the inner tracker. What is the role of AI at EIC? Well, EIC would be one of the first experimental facilities making use of AI since its design phase until the end of the physics program. As you can see, the design phase of the experiment itself will last for the next couple of years. Detector designing, specifically like the EIC general purpose detector, are very challenging because of the high number of detector parameters to optimize. Added to this high dimensionality comes the constraints during the design optimization. These constraints can not only be mechanical but also technological at times. Therefore, finding optimal solutions to such a complicated problem can be challenging. Therefore, AI can play a crucial role in designing these complicated machines. During the design phase, different working groups, like you see here, the detector working group, physics working group, and the computing or AI working group constantly work together, where the physics working group sets the performance benchmarks for the designing problem. Then the computing team takes into those benchmarks and provide a design solution to the detector working group and work with them to find out if the proposed solution can be realized. This information goes back to the physics working group where they can continue reviewing the achievable performance and give feedback. The current setup in HA allows us to follow this workflow and effectively work through the design phase. Here is a typical working scheme on how AI can help steer designing the EIC detector systems. Using AI, one can build more efficient detector in terms of performance and also include costs to be minimized. The shown scheme here can be adapted outside of particle physics community too. For example, designing medical physics detectors with potentially improved performance and low cost. Finally, AI not only fine tunes the optimization but steers the design and will be capable to capture any hidden correlations, if any, among different design parameters. So the scheme is as follows. We inject some physics events, then simulate the detector response corresponding to the physics event and analyze the result of the simulation. Say the resolution, reconstruction efficiency are the ones that gets analyzed. Then using this information, AI can suggest the next interesting design point to explore, and we continue this loop till optimal solutions are reached. HA's tracking system. Here is a Geant4 visualization of the HA's proposed tracking system. As you can see in this picture, which shows the direction of the hadron and the lepton colliding to produce final state particles. The whole detector is split into potentially three regions based on the angle or the pseudo rapidity eta. The eta between positive 8.8 to 4 is termed as the forward region, where eta between 3.5 and up is termed as extremely forward region. Similarly, eta between negative 0.88 to 4 is called the backward region, and the region between negative 0.88 to positive 0.88 is called the central barrel region. The forward direction is also called as the hadron going direction, and the backward is also called as the electron going direction. The tracking system comprises of the inner tracking system, followed by the outer tracking station, and then a set of PID detectors, followed by the time of flight detectors. The inner tracking system comprises of the central barrels. In here, uh, we have a total of 6 barrels, which are further classified as vertex barrels, followed by the Sagitta layers. The Vertex and the Sagitta will use the latest silicon ITS3 technology for improved resolution and less material thickness. The inner tracker then is followed by the outer layers made of gaseous detector, namely the microarvel. The forward and the backward region comprises of FST, which is made of silicon technology again. This is basically the inner tracker. Outside of this inner tracker, we've got a set of additional tracking stations, namely the outer tracking stations, the gem detectors, the forward gem and the backward gem, and in the central region, we have another layer of microarray. Then we have a set of PID detectors, DIRC in the central region, DRICH in the forward region, and MRICH in the backward region. Then we have the time of flight detectors, namely the ETTL, CTTL, and the FTTL. All these detectors shown here collectively contribute in the tracking of charged particle in HA. The main one, of course, being the inner tracker. Consider only the inner trackers. You can see this design is symmetric on both forward and backward region. However, the design can be asymmetric, and those designs are also considered during this optimization project. For simplicity, let us discuss the symmetric case and assume the backward disks take the exact magnitude of Z but in the backward region. The geometric parameters have significant impact on the performance of the tracker. A detailed parameterization was done to basically reduce the real dimensions of the problem. For example, the minimum radii of the disks had to be compatible with the increasing radii of the beam pipe in either direction. So, placement of disk in Z will decide the R minimum of the disk. Similarly, the length of the barrels cannot be changed arbitrarily. Specifically, for the Sagitta and the vertex layers, they come with fixed length, and that is mostly due to the manufacturing constraint. Here is the silicon vertex tracker that uses ITS2 technology that was built by the Alice collaboration. We intend to reuse these staves, and therefore the lengths of these layers are fixed. Also, the mechanical support structures, along with cabling and servicing, had to be made compatible for every new design that we explored. These constraints can also be parameterized. After all parameterization in this problem, we have a total of 11 independent parameters which were deduced, which could potentially be changed and optimized. The performance of the inner tracker is characterized by its detector response, that is, the momentum resolution, the position resolution, the vertex resolution, the reconstruction efficiency, etc. for the tracks. Multi objective optimization can be summarized relatively easily. Consider the problem in hand. The performance of the tracker is not determined by a single measure or a metric, rather, the performance is characterized by more than one objective: the momentum resolution, theta resolution, etc. This problem could become challenging as the objectives conflict with one another. Say, for example, arranging the detectors in close proximity in this case could yield a better position resolution. But if you have a larger lever arm, the momentum resolution could be better. Therefore, these objectives are conflicting in nature. We also have various geometric constraints to consider. Therefore, to solve such problems with or without constraints, give us a trade off solutions known as the Pareto optimal solutions. Consider the picture here. Consider two objectives F1 and F2. The points here are the evaluations done on the problem using different design parameters. A and B are solutions to this problem and they reside in the Pareto front. Therefore, they are called as Pareto front solutions. Say the task in hand is to minimize the function f1 and f2. Then A performs better in the objective f2 compared to B, but on the other hand, B performs better than A in the objective f1. Therefore, these solutions are equally optimal compared to the solution here, say for example C, which performs poorly than both A and B in both objectives. Therefore, solving multi-objectives means converging on a set of Pareto optimal solutions where all the solutions are equally optimal. Here is the petal diagram used to visualize the solution to the tracking problem. The blue and the orange petals are the ratios of the AI suggested design point resolution to the baseline. So, smaller the radii, better the performance of the new design point. The green petal is the Kalman filter inefficiency, which is a measure of the new solution in its absolute scale. Due to the multiplicity in solutions, evolutionary algorithm is an intuitive choice to explore. Therefore, we had developed a pipeline for this optimization using PyMove and Fun for All, which is a framework which is based on Giant that is developed by BNL for end-to-end particle physics analyses. Elitist non-dominated sorting is a method that performs non-dominated sorting of the solutions. For the teeth call, consider the population and the offspring which are evaluated with a fit function f. They cross over to produce a set of RT population, which are then sorted and ranked based on their position in the objective space into fronts. The top ones here, F1, is the least dominating solution, followed by F2 and F3. The dotted line here represents the offspring for each generation that we had requested, and the solutions in F3 are equally ranked. Therefore, a crowding distance sorting is used to select out the remaining offspring, which then goes on to the next generation or call. NSGA2 algorithm has been widely used for various design based problems. Here's how the optimization works. We use NSGA2 algorithm to suggest new design points. Then we simulate the new design point in the Giant 4 based framework, which is Fun for All. Once that is done, we perform an analysis on the result. So for the problem in hand, we have three objectives, namely the momentum resolution, the theta resolution, and the Kalman filtering inefficiency. This is a measure on the ability of tracking reconstruction. Without much math, these resolution measures are a ratio with respect to the baseline detector that is currently proposed in HA. The errors on these fits and the resolutions are promptly carried over into the calculation. As mentioned, the problem also has geometric constraints. The outermost barrel layer should be less than 51 centimeters. The maximum outer vertex layer, which is the second barrel layer, should be less than 15 centimeters. The fourth layer should be less than 45 centimeters in the barrel. The forwardmost Z has to be less than 125 centimeters. The minimum distance between any two layers or discs should be greater than or equal to 1, which gives some room for service. Finally, once we have the optimal set of solutions from this optimization, we can then validate our solutions against other objectives which doesn't get into this optimization, namely the vertex resolution, the reconstruction efficiency, etc. Now, since we discussed all the ingredients for the pipeline, here I explain the software stack that was developed for this problem. We made a modular framework to be as flexible as possible. This pipeline has been implemented in JLab Slurm nodes. We have a wrapper wherein we initialize the design population. A set of 11 random numbers corresponding to each design point is initialized to each of the gene in the population. These random numbers are generated with some constraints such that the solutions do not become unphysical during the detector simulation. Also, to accelerate the evolution towards convergence, one of the gene or one of the design point is modified to have the baseline parameters of the detector. Then we have the multi-objective optimizer, in this case PIBO, where the genes are evaluated. For evaluating the genes, we deploy two-level parallelization. The initial parallelization evaluates the design point, that is, it runs the Geant4 based simulation. Again, at this level, we parallelize again the simulation on a thread level. Once when the simulation is done, then we analyze the simulated detector response for the design point using the procedure that I just outlined before. The evaluated objectives along with the design points are then passed into the NSGA2 algorithm, which yields new set of offsprings to explore in the next iteration. Our problem in hand has 11 variables at least. If we consider the asymmetric design, then the parameters will increase. We have been running optimizations up to 15 parameters corresponding to the asymmetric design too. For this problem, however, we have three objectives, and then we ran with a population of size 100 and with offspring distributed over 50 physical cores. As this software stack is modular, we can plug and play at different stages of the pipeline. The main resource overhead is in the simulation of events, and as you can see, it takes about 80 minutes to simulate 80,000 events. Currently, the genetic algorithm and sorting takes negligible time for computing. But preliminary studies, as expected, scales nonlinearly as the population size increases. To reduce the resource overhead, options like DASks are currently being explored and is currently being implemented to exploit the JLab allocated resources for EIC to the fullest. Also, the framework can be with ease switched to other Mo optimizers like MOBO, which stands for Multi Objective Bayesian Optimizer, like BOTARS for optimization. Here are the results of the optimization. The top left one is the convergence plot, where I plot the hypervolume as a function of number of function evaluations. As the optimization converges, the hypervolume becomes a constant. On the bottom left are the approximate Pareto front solutions corresponding to the final call or the final generation. In this 3D plot, the axis represents the three objectives, namely the ratio of momentum resolution, ratio of theta resolution, and the absolute value of Kalman filter inefficiency. The blue star point here represents the chosen solution after a manual post hoc decision making process. On the right bottom, we see a petal diagram which represents the performance of the chosen blue star point in its three objectives that we optimized. And finally, on the top right, we show the Geant4 visualization of the chosen solution. Here is a more quantitative comparison of the chosen design point's performance against the baseline. The top row here shows the momentum resolution of the pi minus tracks in various eta bins in the central and the forward regions. The dotted gray lines show the physics working group requirement for those eta bins. And the plots on the second row is the ratio of the AI suggested point to the baseline. We seem to have about 20% improvement in the central region and under the physics requirement in the central region. We have about 15% improvement in the forward region between eta 2.5 and 3.5. Similarly, for the position resolution theta, we do see an improvement in the final eta bin between 2.5 and 3.5. The plot on the top is a measure of relative Kalman filter inefficiency in bins of pseudo rapidity eta and generated momentum p. The red numbers here denote the optimal Kalman filter inefficiency improvement with respect to the baseline, and the blue denote the baseline Kalman filter inefficiency. The colors in the matrix represent relative improvement. The more darker the color, we have an improvement in Kalman filter inefficiency with respect to the baseline in that bin. We can observe that the eta region between 1 to 2.5 has good improvement, and this region has the transition region where we transit between the barrel to the discs. The bottom plot shows the validation of the reconstruction efficiency in bins of eta. we do see that we still perform in par with the baseline design, and that is and we have a consistent improvement with the last intervene. Here are more validation checks on the phi resolution where we find that the result is not underperforming even when these objectives were not part of the optimization. Finally, that is not all of the story. We have multiple AI based pipelines with different tracker concepts, symmetric, asymmetric designs with combination of different technologies being explored. As mentioned, this is how AI suggests new design and even new technological designs for the tracker. The developed pipeline has been successful in handling all of these variations and has been stable throughout the optimization. In conclusion, EIC is one of the first experiments to be designed with the support of AI. HA is leading these efforts with an unprecedented attempt in detector design. For the first time, such a framework integrating detector design using multi objective optimization and Geant 4 based detector simulation has been developed. The developed framework can massively be parallelized too. The pipeline is stress tested and is running stable at JLab Slurm nodes. Multiple detector concepts are being explored. More exciting detector designs and ideas are yet to come in the coming months and years. AI, not only in this front, helps us simply optimize the geometric parameters, but rather assist experts in steering the design and the choice of technology during the design phase. I would like to show and emphasize the evolution of the design of the inner tracker since we started back in May of 2021. The new baselines are being steered as an outcome of AI based researches for new optimized solution. The framework yield approximate Pareto front solutions. Cost parameterization is complicated, but it can be done with some reliable parameterization, then it can potentially be included in the objectives. This is one of the reasons post hoc decisions are made with various Pareto front solutions. As mentioned, asymmetric designs are also being explored with different parameterizations, and it has about 15 design parameters to optimize, which is currently running at JLab. Finally, I would like to end with a message. AI can not only fine tune optimization, but can indeed assist in development of the detector during the design phase. Also, this does not limit itself to particle physics detectors alone, but the concept along with the framework can be adapted relatively easily into other fields like the design of the detectors for medical imaging or designing detectors that are used in the field of radiation oncology. Thank you for your patience and thank you AISIS for giving me an opportunity to present my work at this conference. Thank you all.